All right, hey everybody. Today we're going to be taking a look at a topic called isometries in the plane. And this is a topic that is covered in a little more detail, say in a linear algebra class usually. We'll just be breezing through it, but it will be important to us, especially in the videos to come. And in particular, we are going to be looking at functions that we haven't really looked at yet. And these are functions from R2 to R2. So whenever you see a function today, or a function in this video, we're going to be thinking of it as a function whose inputs and outputs are both elements of R2. And so of these kinds of functions, there is an important definition, an important subclass, and these are the so-called isometries. And so very formally, an isometry is a function, specifically in our case from R2 to R2. An isometry is a function for which, if I take any two elements in R2, which I'm writing as vectors a comma b, so if I take any 2 points a comma b and plug them into f, the result will satisfy the following definition, or the following equation, where f of a minus f of b, the norm of that will equal the norm of a minus b. And just as a quick reminder, all of these objects, a, b, f of a, and f of b, are elements in R2. So these are vectors. And when I have two vectors, if I subtract one from the other, what I get is the displacement vector. And if I take the norm of that, the norm of that, what I will get is the distance between those two vectors, or in this case, the distance between the 2 points described by a and b. So what I'm really saying here is the distance between the 2 points a and b will be equal to the distance between the 2 points f of a and f of b. So if I take any 2 points in the domain, the distance between them will not change after I plug them into the isometry. And indeed, that's where the word isometry comes from, right? Unpacking that a little bit, we have iso, which means same, and metry, you can think of that as sort of metric, right? Measuring distance. So an isometry is a function that preserves distance between points in R2. All right, let's look at some examples. Right, example 1, I have two functions here, f and g. So in example 1, we have f of x comma y equals x comma y plus 1 comma 1. Right, so again, this is a function whose input is in R2. The output is in R2 as well. And to graph two, sort of pretty easy, or to calculate and then graph two easy points, we have f of 1 comma 0. That's just going to be 1, 0. Plus 1, 1, but of course that just becomes 2, 1. And similarly, f of 1, 1 becomes 1, 1 plus 1, 1, and that's just going to be 2, 2. All right, so if I wanted to graph this, right, we don't have a great way to graph functions from R2 to R2, but schematically, I could graph, here's my xy plane. I'm going to plot the points 1 comma 0. Here's the point 1, 0. Here's the point 1, 1. Right? And then after I plug these 2 points into the function, I'll get these as outputs. So let's graph those. So after plugging in the point 1, 0, what I get is the point 2 comma 1. So that's going to be this point right here. Right, that's 2, 1. And I could think of my function as being the function that sends this point up to this point. And similarly, if I plug in 1, 1, I'm going to get 2, 2 as an answer. And my function sent this point up to this point. So that's sort of a quick way to sort of plot how my function worked in this case. And we can see, at least intuitively, this function is an isometry. Notice if I measure the distance between f of a and f of b, right? So if I measure the distance of this dotted line, that is going to be the same length, the same distance as from this point to this point, the same length as this dotted line here. So those two lengths are going to be the same. We can really, again, intuitively, but we could make it more rigorously, show that given any 2 points that I want to graph,
well, we'll cut that.
And again, it's relatively intuitive to see, although we could show it more rigorously if we wanted to. But it's relatively intuitive to see that given any 2 points in the plane, say this point and this point, if I plug them into the function, I'm just going to add 1, 1 to each of them, and the distances between them will be preserved. So this function will be an isometry. Now, let's compare that to this function down here, which we'll pretty quickly see is not an isometry. So we have the function g of x comma y equals 2 times xy. And again, g of 1, 0, well, that will become 2, 0 by scalar multiplication. G of 1, 1 will become 2, 2. And what we see is that if we go to graph this, right, I had the point 1, 0, I had the point 1, 1, I have the distance between them, and then I plug each of those points into the function, and what I'll get is the distance, or the point 2, 0, the point 2, 2, and the distance between them. And we can see that distance has not been preserved here. This is not an isometry. All right, so it turns out, let's go back a second. It turns out that an isometry can largely be thought of as rigidly translating the plane, reflecting the plane, or rotating the plane. And we'll see in a little bit that these are really the only options when it comes to an isometry of the plane. For example, let's find it again. Here it is. In this example here, right, the example F, where we're adding 1, 1 to every point, I can think of this as taking every point and adding 1, 1 to it, sort of as individual points. Or I could think of it as taking the entire plane and picking it up and moving it in the 1, 1 direction and sort of rigidly moving it over up 1 unit to the right and 1 unit up. So this is thought of as an isometry of the plane, specifically that's being described by a translation of the plane, by dragging it over and up. To see this another way, look at this high-tech piece of paper that I have here. Imagine this is the plane with 2 points drawn on it. We can see immediately that if I have any function that describes a translation of the plane, just by moving it up here, that the distance between these 2 points, and really any 2 points in the plane, will be preserved. Similarly, a rotation, right, sort of rotating everything like this, will be preserved. The distances, I should say, would be preserved. And finally, a reflection, right? If I were to take this plane and reflect it along, say, the y-axis, then the distance between the 2 points would still be preserved, and the distance between any 2 points would be preserved. Okay, so with that in mind, I want to come up with a nice way to describe these isometries, to describe these functions. And the best way to do this is to use our vector and matrix notation. All right, so we're going to be using our vector notation for points in R2. We'll let x comma y be written instead as this column vector xy. In this case, translations, like the one we just saw, could be described as f of xy equals xy plus some constant vector, for example, 1, 1, and that's describing a translation of every point by this vector c1, c2. A rotation vector, or I should say a rotation matrix, can be used to describe the act of rotating the plane. Right? So specifically, a rotation can be described using the function f of xy equals a negative b, ba, this matrix, times xy. Right? And maybe quick, check to make sure, this does in fact give us an element of R2, right? So we plugged in an element of R2 as an input. The output is also an element of R2 by our matrix multiplication. This becomes AX minus by as our top entry, and then bx plus ay as our lower entry. Right? So in particular, this is still an element of R2 written as a column vector. So it's a function that takes elements of R2 in and spits out elements of R2. So we're good to go. It is, and I should say, it is a rotation matrix if it has this form and if we have a squared plus b squared equal to 1. That will be a rotation matrix that describes a rotation in the plane. All right, and then finally, we have our reflection action as well. And the reflection action can be described using a specific matrix. Let's use the matrix 1, 0, 0, negative 1. And indeed, another quick sanity check that when we do this, this will give us x up here and negative y down here. So we can really think of this as a reflection across the x-axis, right? The x-coordinate won't change, but the y-coordinate will go from y to negative y. And so this is a reflection specifically across the x-axis. So these are our three big isometries. And indeed, any combination of these isometries will result in a new isometry. So for example, if I were to take my plane, translate it, rotate it, and then reflect it, what I would get is still an isometry. And so we'll state this as a theorem, although we won't prove it here. It's really a theorem of a linear algebra flavor. But we'll state as a theorem or as a fact that every isometry of the plane can be described using a combination of translations, reflections, and rotations. And we can see this as follows. Specifically, I should say that specifically we can write this as follows. For our function that's an isometry, f of xy, we can write it as a matrix A times a matrix B times the vector xy plus an additional vector c. And specifically, our vector A corresponded to our rotation matrix from before. Vector B has one of these two options. So it's either our reflection that we described before, or it's the identity matrix, which doesn't change anything, which leaves everything the same. And finally, we have C, that is a translation by a certain amount. And this will describe any and all isometries of the plane.